In this video, we're going to apply the Maclaurin series expansion formula to a few of our favourite functions. So let's start with a real classic, e to the x. So the nice thing about e to the x, the thing about e to the x is that every derivative is just e to the x. So this is a very, very, very easy one to work out the Maclaurin series for. So all of these are just e to the x, and so on, which means that f of naught and f dash of naught, they're all the same. When you sub in naught, you just get 1. If you sub in naught here, you just get 1. If you sub in naught here, you get 1, and so on. And what that means is e to the x is approximated by this polynomial. In fact, it is this polynomial if you send it to infinity. F of naught is 1. F dashed of naught is 1, so that's 1x. The second derivative of at naught is 1, so it's 1 times x squared over 2, or x squared over 2 factorial, and then it's 1 times x cubed over 3 factorial, and then it's 1 times x to the 4 over 4 factorial. Now, this might even be a result that you've seen before, and it's pretty cool, I think, to be able to see where it comes from now. So that polynomial is, if you let it go to infinity, is e to the x. Let's have a look at that in GeoGebra. So here's y equals e to the x. And then let's start looking at the polynomial. So if I do y equals 1, well, that's correct, at least it gives the right y-intercept. Plus x, it's now got the right y-intercept and the right gradient. Plus x squared over 2, it's now got the right curvature as well. Plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, plus x to the 5 over 5 factorial, and so on. And you can see that our polynomial is sticking to e to the x for longer and longer. It just trails away here quite quickly, but over on this side, it really does stick to it really well. So that's e to the x. Let's have a look at sine x now. So to find the Maclaurin series, we're going to need a stack of higher derivatives. So the first derivative is cos x. The next derivative is minus sine x. The next derivative is minus cos x. And then the fourth derivative, we are back to just sine x. And so this one repeats. It's periodic. It just goes sine, cos, minus cos. So what we can say is that the function at 0 is sine of 0, which is 0. Then the first derivative at 0, cos of 0, is 1. Then minus sine of 0 is 0. And then minus cos of 0 is minus 1. The fourth derivative is 0 again. So this one cycles 0, 1, 0, minus 1, 0, 1, 0, minus 1. And so our Maclaurin series is pretty straightforward. So sine x is, well, it's f of 0, which is 0. I don't bother writing that down. And then f dash of 0, which is 1 times x. So it's 1 times x. Then it's the second derivative, but that's 0. Then it's the third derivative, minus 1 times x cubed over 3. So minus x cubed over 3 factorial. Then the fourth derivative, which is 0. The fifth derivative would be 1, so that would be plus 1 times x to the 5 over 5. The sixth derivative would be 0. The seventh would be minus 1, giving us minus x to the 7 over 7 factorial. And we get this beautiful pattern here where the polynomial expansion of sine x is we just work through the odd powers of x, alternating positive negative. So positive x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. So let's have a look at that in GeoGebra. So here's y equals sine x, and if we start spelling this out, our first term was x, giving us the right y-intercept and gradient. Then minus x cubed over 3 factorial, and it sticks to our sine curve a bit longer. plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial, plus x to the 9 over 9 factorial. Let's stop there. So it's pretty nice to see this function just snaking its way along the sine curve for so many values. Let's do cos x now. This is going to be very similar. So f dashed of x is minus sine x. Then the second derivative is minus cos x. The third derivative is sine x. And then the fourth derivative, we're back to cos x. So this is another periodic one where it cycles. So cos minus cos sine, and repeat. So evaluating these at 0, we have f of 0 is 1, right? Cos of 0 is 1. Then minus sine of 0 is 0. Minus cos of 0 is minus 1. Sine of 0 is 0. And we repeat. The fourth derivative, cos of 0 is 1. So these terms are going 1, 0, minus 1, 0, 1, 0, minus 1, 0. That means that cos x is, well, f of 0 is 1, so we start with 1. F dash of 0 is 0, so we don't bother. The second derivative is minus 1, so it's minus x squared over 2. I can write the factorial. We don't need to because 2 factorial is 2, but I think it's nice to see the pattern. The third derivative at 0 is 0. The fourth derivative is 1, so plus x to the 4 over 4 factorial, and the pattern continues. We skip over x to the 5 because the fifth derivative of cos is 0 at 0, but then we do have the sixth, but it's negative. So just like sine, it's alternating, positive, negative, and also just like sine, it skips over every other one. It's just cos does the odds and not the evens. And so this is our Maclaurin series for cos. Let's have a look at that in GeoGebra. So if we start with y equals cos x, and let's have a look at our expansion, y equals 1 minus x squared over 2 plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on, minus x to the 10 over 10 factorial. So there we have it again, our polynomial curve snaking its way along the function. Let's take a look at one more now. We have y equals ln of 1 plus x. So we actually differentiated this a couple of videos back, so you can refer to your notes, but to do it again, the derivative of that is 1 over 1 plus x, or 1 plus x to the minus 1. Then the second derivative is minus 1 plus x to the minus 2. The third derivative is minus 2 times minus 1, so 2, 1 plus x to the minus 3. The fourth derivative, I mean, look, in an exam question they tell you how far to go, but let's just explore this for fun. Minus 6 times 1 plus x to the minus 4. Let's just do one more. So the fifth derivative is 24, 1 plus x to the minus 5. So evaluated at 0, f of 0 is ln of 1, which is 0. Then everything in these brackets is always just going to be 1, because 1 plus 0 raised to any power is always 1. So we've just got 1 here. That was the first derivative. The second derivative at 0 is just minus 1. The third derivative is 2. The fourth derivative is minus 6. And the fifth derivative is 24. So what have we got going on here? Well, our f of x, which was ln 1 plus x, is f of 0, which is 0, and then it's 1x, so it's x. Then minus x squared over 2 factorial, so minus x squared over 2 factorial. Then plus 2 times x squared, x cubed over 3 factorial. Plus 2 times x cubed over 3 factorial. Then minus 6 over 6 x to the 4 over 4 factorial. Then plus 24 x to the 5 over 5 factorial, and so on. Now, can we simplify that? Well, we can, because look, this one's fine, x squared over 2. But what is 3 factorial? It's 6. And 2 over 6 is a third. So that's plus x cubed over 3. And what is 4 factorial? It's 24. And 6 over 4 is a quarter. So minus x to the 4 over 4. If you know your factorials, you'll know that 5 factorial is 120. And 24 over 5 is a fifth. And you'll see there's this beautiful pattern here. X minus a half x squared plus a third x cubed minus a quarter x to the 4 plus x to the 5 over 5, and so on. So another beautiful pattern there. Let's explore that one in GeoGebra as well. So y equals ln of 1 plus x looks like this. And let's explore our Maclaurin series. So it began with x, and then it was minus x squared over 2. Then it was plus x cubed over 3. Then it was minus x to the 4 over 4. And plus x to the 5 over 5. Minus x to the 6 over 6. And so on. Plus x to the 7 over 7. Now, you might actually notice something about this, that in this range, this one looks really, really good. But it really quickly diverges, and I actually added quite a lot of terms and it still wasn't kind of getting any better. So if I add minus x to the 8 over 8, maybe another one, plus x to the 9 over 9, it's not sort of sticking to the function in the same way that e to the x and cos x and sin x were. Now there's a reason for that. That's that this one is actually only valid between minus 1 and 1. The full reasons for this are slightly complex, but just notice that the original function ln of 1 plus x definitely does not exist at minus 1 or to the left of that, because then you'd have ln of 0, which is not defined for real numbers, and or rather it's not a real number, and yeah, ln of 0 undefined, and ln of negative numbers not real. So the function definitely disappears there. So we know everything to the left of that has to be discarded anyway. Basically, if it goes wrong at 1 unit to the left, it will also go wrong at 1 unit to the right. That's an informal reason why this one doesn't work. So just bear that in mind. Some Maclaurin series are valid in theory for all values. Others have what's called a radius of convergence. And this one is only valid between minus 1 and 1. So what we'd say is that this thing here is only true when mod x is less than 1, meaning it's between minus 1 and 1. Okay, so that is the process of finding Maclaurin series for different functions, and we'll explore this more and in more detail in the next video.